Make sure the audio's good and the Twitch feed's coming in and everybody's happy. And let's see who we got in the Mr. Hoke, Mr. Ivy, Mr. Hall, Mr. Adams, a bot named Another TV Viewer, whoever Lurks is, Lurks with two X's. Welcome, enchanté. All right, so let's get to it. So last time we went through a couple more examples of floating point numbers. So what I thought we would start with is actually just let's put you guys to work. And let me switch over to the Elgato on here. So what I'd like you guys to do is do two quick exercises. Okay, so let's do two quick exercises. So just we'll take a few minutes and you guys work them out on paper, and then we'll see what we get. So take the number 1.375 and encode that as a float 8. And then to go the other direction, let's take the number 10101010. Okay, so it's kind of an interesting looking pattern. Or in hex it would be AA, and take that and decode it, assuming that it's a float 8 to begin with. Okay, so we'll do both directions, and should put on the Jeopardy music. So take a couple minutes and work these out, and let's see what you get. S'il vous plaît. This constitutes being awake, Mr. Connect Car. Wake up. Isn't this fun? I think so. Yeah. Well, if you don't get it right, that's okay. That's why we're here, is to learn, right? While you guys are doing that, I'm going to print out the revised seating chart since we've moved over here. All right, is the seating chart made it all the way around? Almost. Yeah, no, you're fine. Um, yeah, you guys would be here and here, or no, here and there, and then he's on that row. All right. Well, let's get to it. So how do we do the first one? What's the first thing we got to do? Yep. Okay, the sign. That's a good place to start. What is it in this case? Yeah, so the sign is positive, so the sign bit is a 0. Okay? Oh, well, what else do we need to do? Well, how else? We need to first write 1.375 as a binary number, right? And so 1.375 in base 10 is, and I picked 375 because that's 1 plus a quarter plus an eighth, right? Okay, which means it would be 1.011 as a base 2 number. Okay, are we cool with that? Okay, because what do we have? We've got a quarter and an eighth, and no halves, and nothing beyond that. Okay, is that okay? Now, let me go ahead and add a 0 at the end there, um, because what therefore is our mantissa? Yeah, it's the stuff after the radix. Okay, and in this case, did I have to shift the radix at all to get this in sort of proper form? No. Okay, so what is the exponent? Right. But it'll look like 3, okay, because of the exponent bias. Because remember, the exponent looks 3 bigger than it actually is. Okay, so the exponent field is going to be what in binary? Right, 0, 1, 1. Okay, so that's there. And then my sign bit was here. Okay, so the encoding is sign bit 0, exponent 0, 1, 1, mantissa 0, 1, 1, 0. So that part went here, this part went there, and that part went there. And what is that in hex while we're at it? 3, 6. Yes, good. Ah, well, the exponent is 0 because how many positions do I need to move the radix here? None. Yeah. So like let's say that the number was 2.375, then it would have been 10 dot stuff, right? But how do we have to write things in scientific notation? Precisely one digit before the radix. So we didn't have to do any shifting here, and hence the exponent's a 0. Okay, is that all right? Yeah. Now, not always is that the case, right? This is just because of the number I picked, but it could have been um, that. Yeah. Okay, good. All right, what about the decoding side? So I picked just a pattern, a repeating pattern here, just for funsies. Okay, so first off, let's pick out all three of the parts. So what's the sign bit here? It's a 1. So whatever we're encoding is going to be a negative. The exponent is what? 0, 1, 0. And the mantissa is 1, 0, 1, 0. Okay. So the exponent, what does 0, 1, 0 look like? Looks like 2, but it'll count as negative 1 because the exponent always looks 3 bigger than it really is, okay, because of the bias. Okay, is that all right? No? All right, so what about the mantissa? So what I'm going to do is I'm going to write 1 point mantissa times 2 to the negative first. Okay, so I've sort of written it in pseudo-scientific notation. Okay, and then what does multiplying by 2 to the minus first do to the radix? Moves it to the left one position. Okay, um, this is the binary equivalent of 90% off at Kohl's. Okay, and so we have this as our number. Okay, are we okay so far? Any questions, preguntas or fragens? 9? We have 9 questions. Okay, so then what? Well, we just need to figure out the place value of everything, right? So what do we have here? We've got a 1 in the which position? Let's start from the left and work right. We got a half. We got a quarter. Do we have an eighth? Nope, but we do have a 16th. Okay, so whatever this number is, we got a half, we got a quarter, and we got a 16th. What does that all add up to? That'd be what? Yeah, so this would be 8 sixteenths plus 4 sixteenths plus 1 16th is 13 over 16, which is 0.8125. Okay, so if we put all this together, what does our number here actually represent? It's 0.8125, but it's negative because our sign bit, right? So now we get to take that into account. Oops. Okay, so it represents negative that because our sign bit was a negative. Okay, so this is sort of one thing about floating point that's kind of nice. If you want to negate something, what do you have to do? You just have to flip the sign bit. There's none of the flipping everything and adding one stuff like we have to do with integers. You just have to flip the sign bit. So that's kind of nice. Okay, questions, issues? This kind of starting to sink in, hopefully. All right, so now that we're hopefully getting more comfortable with the encoding and decoding part, the next thing we want to do is talk about how to do arithmetic with floating point numbers, right? So how do you, well, might as well start with addition, right? How do you add floating point numbers, okay? And in order to start that discussion, let's actually go back to how to do this in sort of normal base 10 arithmetic, and then we'll analogize back to base 2, okay? So, all right, so floating point arithmetic is the name of the game today. All right, so for, like I said, for right now, let me just work in base 10 for, just so we can exploit y'all's familiarity with regular arithmetic. And let me just make up a couple of numbers. So I'm going to make up the number 3.7 times 10 to the second, and I want to add to that 4.2 times 10 to the first. Okay. All right, so what really am I doing here? I'm doing 370 plus 42, right? But I'm doing it as floating point. Okay, so so that would be one way to do it, is just decode both of these numbers, do the addition sort of the usual way, and then re-encode the answer. Okay, so if we did that, what did we say we were doing? We're doing 370 plus 420, or sorry, plus 42, which would be what? 412? All right, and what is 412 in scientific notation? It'd be that. Okay, so ultimately that's where we should get. But the process of how we get there is the sort of meat of the discussion. Okay, question, preguntas, and or fragens. 9? Okay, good. So now what? Well, let's take our two numbers. Which of them is bigger? The 3.7 one, right? And how do you know it's bigger? Because it has a bigger exponent. Okay, you know instantly that that's the bigger number. If the two exponents were the same, how would you tell which number's bigger? You'd have to look at the stuff before the exponent, right? You'd have to look at the mantissa parts. Okay, but we don't have to do that here because the exponent makes that obvious. Okay, so what I need to do is I cannot add two numbers that have different exponents like that. I can only add them once they have the same exponent. Okay, and so what I want to do is I want to deliberately denormalize one of the numbers and make it have an exponent that matches the other number. Now, there's two ways I could do that, right? I could think of the first number as being 37 times 10 to the first, or I could think of the second number as being 0.42 times 10 to the second, right? So which way do I want to go? Now, when you do this on paper by hand as a human, it actually doesn't matter which way you do it, right? But it'll turn out that on a computer, like on a computer, how many bits do we have for our mantissas? We only have 4. That's it, right? And so what that means is if you accidentally lose a bit, would you rather lose a bit that represents a really big thing or a bit that represents a really small thing? you'd probably want to lose the stuff that represents something small because that means you lose less precision. So in base 10, this would be like, imagine that you would have to lose a digit here. Would you rather lose the 3 in 3.7 or the 2 in 4.2? You'd much rather lose the 2 in 4.2 because then your answer would be 410 instead of 412. That's not that far off. Whereas if you lost the 3, you'd be looking at 112 versus 412, which is a huge difference. Okay, so if you're going to lose precision, you want to lose it at the smallest place value possible. Okay, so what that means is that we want to leave the bigger number, the bigger number alone and only mess with the smaller number. Okay, so I'm going to denormalize this one, and I'm going to think of the problem as really being this. Okay, so you guys see how I wrote 4.2 as 0.42 times 10 to the second. Okay, first off, do you agree that those are the same thing? Mathematically, I mean. Okay, they obviously look different, but mathematically they're identical. Okay, and remember that the second number there, the 0.42 thing, is denormal because what should there be before the decimal point? There should be precisely one non-zero digit. Here there is not. Okay, hence that thing is not normal. Okay, now that I've written it in that form and the exponents match, what do I get to do? I get to think of this like that. Okay, both terms, both things that I'm dealing with, have the same exponent term, and what that means is I can factor it out. Okay, so just a little bit of algebraic trickery.
So with the way that exponents work, like when you add 3,
Mm-hmm.
or like when it's 3 less than it actually is, does that mean you can do fewer numbers in the negative side? Like you can only go to like, would you only be able to go to?
No, because we use a separate bit to encode the sign. I think what you mean is, can you use, so, okay, if your exponent looks 3 bigger than it is, the biggest that it actually would look is 7, right? 111. So the biggest that it can actually count is 4. Well, what's the smallest your exponent could look like? All zeros. What would that count as? It's minus 3. Okay, so the smallest exponent you can have in our system is from minus 3 up to 4. Okay, so that doesn't mean that you can represent more positives and negatives. What it means is that you can represent more positive exponent things than negative exponent things.
So why isn't 9 the most? Because 9 minus 3 would be 6 and 4 2 1. Or 7. 11.
Well, yeah, you just answered your own question, right? 7 is the biggest thing you can write down, but what does that count as?
Oh.
Right? 4 2 1 is 7, minus 3 is 4. Right? Okay. Well, in 8 bits, right? Obviously, this is different in others. Okay, so does it make sense here that once I've got the exponents the same, then this algebraic factoring is permissible? Okay, and then what do I have to do? I just have to do normal arithmetic in the mantissa section. Okay, and what do I get there? Well, I would get 4 point what? 12, and then that's times 10 to the second. Okay, the number in this case, okay, after I've done that addition, is the number normalized. Is this in proper form? Yep, so I don't have to do anything. Okay. Sometimes it will happen that when you do that, so like let's say for example that I was adding 9.6 to itself, okay, then what's going to happen? I'm going to, what's 9 plus 9? It'd be 18, right? And if I had 18 point something, then I would have to renormalize the answer. Didn't have to do that here, so no issue. But in theory we could, and we'll run into an example of that, I'm sure, as we continue. Okay, does that make sense? Now, what's going to make this a little tricky in binary is that do we explicitly write down the thing that's before the radix? Or sorry, do we explicitly store that in our binary number? No, because it's always assumed to be a 1. However, when we do the arithmetic, we need to know that it's there and use it accordingly. Okay, does that make sense? Okay, so let's take why don't we take our two examples from the previous sheet? So let me slide back over here. We had 1.375 and we had the negative 0.8125. Let me just make the negative a positive for sake of convenience, and we'll use those two numbers and do the addition of them. Okay, so all right, so binary 1.375 and 0.8125. What was 1.375? What was its encoding? Can somebody remind me? Yeah.
It was 0, 0, 1, 1, 0, 1, 1, 0.
Okay. And the other one was,
0, 0, 1, 0, 1, 0.
okay. So all I did was I took the 0.8125 number that we had on the last example. The last example was a negative. Just for sake of convenience, I'm going to make it positive this time um, for now. But all that means is that I have to flip the sign bit. I don't have to change anything else. Okay, so that's nice. Okay, good. So what I want to do is I want to add these two numbers. Okay. All right. So first thing, let's write them as we did before in sort of scientific style notation. Okay. So 1.375 was what? 1 point, what was the mantissa? 0.110 times 2 to the, what's the exponent? What does it look, what's the exponent look like? 3, so it counts as 0. Okay, are we cool with that? Okay. What about the other one? It would be 1.1010 times 2 to the negative 1. Okay, so let's just make sure that we're clear on the parts here. Uh, the exponents, where did those come from? The exponent field. Okay, but keep in mind we have to subtract off the bias. We did that. Okay. The stuff that's after the radix in both numbers is the mantissa field, right? So I just literally copied those down. But what's immediately before the radix in both instances? A 1, okay? And that's the assumed hidden 1 that we get for free in binary that we don't get in any other base. Okay, so are we good with that to start? Okay, so what's the problem with if I wanted to do this addition? Like when we did this in base 10 up above, what's the problem here? Yeah, the exponents don't match, right? So I can't do that little algebraic factoring trick like it did a minute ago. So what I have to do is I have to denormalize one of the numbers in order to get the exponents to match. Which number do I want to denormalize? I'd rather denormalize the second one in this case because he has the smaller exponent, okay? So if I'm going to lose precision, I will lose less precision if I fiddle with the smaller number than if I fiddle with the bigger number. Okay, so the first number we can leave alone, and the second number I'm going to denormalize. Okay, and it would denormalize like so. Okay, because what does it mean to have a negative exponent? That means you move your radix which direction? To the left. Okay, I'm only going to move it as many spots as are necessary in order to get the exponents match. In this case, that was just one spot, so that was easy. Okay. Okay, so we're good up to here. Yeah? Okay, now I can do the factoring trick. So I'm going to take my two numbers, 1.01, sorry, 1.0110 and 0.11010, and I'm going to add them. Okay, so when I do so, now here's sort of something funny. What is this dude there? Where is he? That zero that I put in blue. That's equivalent to this one here. Right? What is that? It's a fifth bit in the mantissa. Do we get to have a fifth bit in the mantissa? No. So what happens to that zero? Poof, he just disappears. Now, is that a problem here? No, because losing a zero doesn't change anything, right? If that had been a one, then this one, a piece of information, would have just been deleted. And that would have resulted in a loss of precision. Okay. When that happens, that's called a truncation error. Okay. So think about it this way. If you have your calculator goes out to 10 decimal points, and you've got two nasty numbers that go out all the way to the 10th decimal point, you add them together, is it possible that things are going to add up in such a way that you lose precision in that 10th decimal point? Yeah, that could totally happen, right? And that's basically what's happening here. Yeah, or could happen here.
You're only gonna get that if it was like 9.10 decimals and then like 7.10 decimals, so it's like a double digit.
Yes.
That's the only way.
Well, that or if when you denormalize, right? Because if you had like 9 point something and 10 points, or sorry, 7 point something, those already are normalized and they have the same exponent, right? So the so that the loss of precision can happen in two ways, right? Either what you just said, whereas the stuff before the radix adds up to more than 10 or more than 1 in our case, right? Or if when you denormalize, some dudes fall off the boat at the end. Okay. Both possibly actually can happen simultaneously, which is even worse. But okay. So what happens to this blue zero? He just doesn't exist. Poof. Okay. And then we add accordingly. And what Cole was saying is about to happen. Okay. So I do the addition, and the far right two places are okay, right? But what's going to happen in the third from the right place where I have a 1 and a 1? So here, 1 plus 1 is 0. Oh, I'm incompetent, guys. Let's try this again. This is what happens when you try and do math in the morning. All right, so 1, 1, 0, carry, 0, carry, 0, carry. There we go. All right, is that all right? Yeah. I was wondering why I was getting funny looks from the peanut gallery. So, I mean, you guys pay how much in tuition, and the best you can, or best you can get is me, right?
Scam.
Yeah, you should go to President Feller and demand like at least a 50% rebate um, for. But I've got class with McKinney, man. You should give me a discount. Okay, so um, so the addition. Are we cool now? Right? What's the exponent that goes with this? The same as what it was with the two numbers here and here after I denormalized, right? That was the whole point of denormalizing, was to get them so that they had the exact same exponent. Okay, so now what we have to do is um, something that we didn't have to in the previous example. Is this result that we have, is that a normalized number? No, because what's before the radix? Something other than just a 1, right? In this case, it's a 2-bit thing, 1, 0. So I have to renormalize my answer in this case. And how do I renormalize that? I just need to shift the radix. Okay. Now, let me actually, instead of thinking about it as shifting the radix, let me instead think of it as I'm shifting the bits, and the radix stays put. Okay, so I'm going to put the radix in exactly the same spot. Okay. Hang on a second, Cole. I know where you're going, but just. Okay, so first off, do you guys see how I shifted all the bits, right? One position to the right. And then because I did that, then I need to increase my exponent by 1. Okay, or Gucci? Yeah. All right, Cole, what's the problem? Oh, you, huh? Yeah. Okay, how many manticibits do we really get? We only get 4. How many things do I have here? So what's going to happen to this 1 on the end? Poof, he's gone. No, because one of them was a 0, so it didn't matter, right? Because the blue bit was a 0. We could have lost it, yeah. Okay, so this bit, poof, because it's in the 5th position after we renormalize. Okay, so what does that mean then for our answer? Our answer is really 1.001 times 2 to the first. What is that, by the way? Well, this would be 1 plus half, fourth, eighth, 16th. So this would be 1 and a 16th, but it's times 2. So really, what is this? 2 and an eighth. So this would be 2.125. Okay, so first off, do we accept that the answer that we got was 2.125? And we'll encode that in a moment. If you had typed all this into your calculator, what would you have gotten? You would have gotten 2.1875. Okay, have we done something wrong? I mean, I know it's before 9 o'clock and my coffee isn't, I haven't finished drinking it yet, but I promise we haven't messed anything up. So what's the deal? We lost precision. Okay. We lost precision due to truncation. So truncation is what you call it when there's a bit that sort of falls off the wagon at the back end. Yes, Cole. Uh, well, it'd be a 16th place in the end because um, while this looks like a 32nd place, the exponent shifts it over to the 16th place, right? So we've lost the 16th place. Yeah, go ahead.
So with the exponents, I'm just trying to understand a little better. When denormalizing it, we like thought about it as moving the radix,
Mm-hmm.
which is why we made it 0, right? Because in the other one we did the exact same thing, but it's 1.
Um,
Like both of them shifted back.
yeah, right. So look, I can think of shifting the radix or shifting the bits, okay? But where you have to be a little careful is shifting the radix one way is equivalent to shifting the bits the other way,
Okay.
right?
So we shifted the radix
To the left, which would be equivalent to shifting the bits to the right,
and then we did the opposite. Okay.
right?
That's what I
Yeah. Yeah, this is why you don't do this stuff at 2 in the morning, okay? Because, yes, right. I mean, you might argue this is why we shouldn't do this at 8 in the morning, but hey, the sun's up, right? At least, so um, yeah. Although, give it what in November when we have to come off of daylight saving and everybody will be screwed up for a month. I really wish we could get rid of that and either just pick we're not going to do like daylight savings ever, or we'll just always do daylight savings. Just pick one, right? I don't care which. Just, huh? Well, no. So, like in November, when the clock shifts, right, we come off of daylight savings and go back to sort of regular time, right? So, either we should just never change it again after November, or never change it at all starting now, in my humble opinion. Okay, so what happened here? We did not make any mistakes, but we got an answer that was different than what we would have expected from a calculator. Okay, why did this happen? Fundamentally, it's because we only used 4 bits for our mantissa. Okay, so we had a truncation error. This is why, by the way, nobody actually uses an 8-bit floating point scheme because these aren't really all that small numbers, right? And we were exposed to this truncation error. Okay. However, this sort of truncation problem still occurs with any other floating point scheme. It's just that the numbers where it happens are much smaller. Okay, because in 16 bits, what was it? You had 5 bits for exponent, 1 bit for sine, so that left of what, 10 bits for mantissa rather than 4 here, right? That's a lot more, and so you get a lot more precision, but you still can lose it in the same way. Okay, so um, the advantage for our purposes of actually using this 8-bit scheme is that it sort of forces this issue front and center into our faces. Okay, is that this can happen? Okay, well, look at that, perfect timing. It's 8:50. So, all right, well, I also posted on Canvas. You guys probably noticed this in the encoding module. My floating point notes, which are still a work in progress. I was making great progress on them in last semester in February and then early March. And then what happened? The world kind of ended. So, anyway. All right. Well, I will see you guys on Friday.